So I want to tell you about functions today, but the first thing I want to talk about is relations, which are precursors to functions. All right, so a relation, a relation is any correspondence between two numbers, is two set of numbers, is any correspondence between two sets of numbers. Okay, so what does that mean? Well, what you can do, so all you need is just a set of numbers, this box here. You have a set of numbers in this box here. So these numbers can come off the x-axis. In other words, the number line, okay? We call that the real line, real numbers. And then these numbers can come off the y-axis. These are also on the real number line. But this real number line is vertical versus horizontal. These are all real numbers, like 0 is right here, and 0 is right here. Same thing as you know before. But so it doesn't matter. Any relation any number can go to any number over here. There's no restriction, okay, at all. The relation just kind of says, okay, well, I'm going to assign 2 to 7 or something like that. I'm going to assign -1 to 4, things like this. So there's no restriction at all. So you could say, maybe a relation could be, for example, in one box could be, now let me make that a little bigger. One box could be some cities, and another box could be states. Now, you could have something like Houston goes to Texas, and let's say Austin also goes to Texas. No problem there. Now, there could be a city, let's say something like San Jose. Now, there's a San Jose, I know there's a San Jose in California, but there's also a San Jose in New Mexico. Okay, so a relation doesn't matter if two of the objects in the first set go to one object in the second, or if one object in the first set goes to two objects in the second set. It doesn't matter. Okay, and the way we would write this out maybe would be Houston, comma, Texas, and then Austin, comma, Texas, and then San Jose, comma, New Mexico, and San Jose, comma, California. All right. So what I want you to notice is that this x value, we'll call it x, goes to two y values. It goes to New Mexico and it goes to California. This can't happen for a function. Okay. So functions. Okay, function. Okay, this is a relation that assigns a unique value y for each x in the first set. So the situation up here with San Jose going to California and New Mexico, this right here, this would not be a function, because for each x, there's a unique y. And this x here, this San Jose, we'll call that x, goes to two different y values here. We'll call these y's over here. Okay, so functions are a little different. Okay, so function is a relation. It's certainly a relation, but it has this restriction on it. Okay, so why does it have this restriction on it? Well, because scientists and mathematicians and engineers and economists and things, they don't like whenever they ask a question. So they ask a question here and they get two different answers out of it. They want a single answer out of each question. So for Houston going to Texas and Austin going to Texas, that's okay. One question, one answer. One question, one answer. But this question, San Jose, goes to two different ones right there. So that's the problem. So what happens with a function is you could have, let me draw this a little different. You could have a set of numbers, let's say people. Let's say people. And let's say these are numbers. Okay, and so suppose the function says, what is the age? The age of each person. So you could have Mary, you could have Jose, and you could have John. Okay, so Mary could be 18, Jose could also be 18, and John could be 21. So age is a good way to remember what a function could be. Now, you can't have it so that Mary is both 18 and 21. She's either one age or she's not. So that's why age is a good way to determine which one works, okay? You can have two things go to one, but you can't have one thing go to two things, okay? So let me draw that a little differently. You could have two things go to one thing. This is okay, but you can't have one thing go to two things. This is not okay. So not okay. All right, so whichever way you can remember that, go for it. So a good example of functions are like y equals 3x plus 1. Any line is going to be a function, except maybe a vertical line. You can have y equals x squared, that's a function. You can have y equals x to the third, that's a function. You can have y equals square root of x, that's a function. So these are all functions because whenever you plug in one value for x, you get a single value for y. So for example, if you look at this one here, if you plug in, let me make this a little smaller. If you plug in one value for x, let's say plug in, let's say 2, you get 4 for y. This is y equals x squared. And if you plug in negative 2, you get also 4. If you plug in 0, you get 0. If you plug in 1, you get 1. If you plug in 3, you get 9. So the set here would be 2, 4, negative 2, 4, 0, 0, 0, 0, 1, 1, and 3, 9. Okay, now let's look at this. Notice that 2 and negative 2 both went to 4. That's okay. Notice that 0 went to 0. That's okay. 1 went to 1. That's okay. All right, so everything's working out great. We didn't have this situation where one term went to two terms, okay? We won't have that here with x squared. All right, so you might be wondering, well, which ones would? Well, we always consider x. So if we let x be what's called the independent variable, then y is the dependent variable. All right, so what does this mean? Well, it means then that dependent variable, you can think of it as this. X always comes first here. Remember, whenever you plug in points, you always plug in points for x. So it's independent. And then y depends on what you plugged in for x. So if that's the case, then we call x the independent variable and y the dependent variable. Plug in numbers for x, y depends on that number. So it's dependent on x. Now, if we consider that same scenario, here's an example of something that's not a function. All right, y squared equals x. So if we're still considering x the independent variable, we're plugging numbers in for x, what happens is you can run into trouble. All right, so let's see. Suppose we plug in 9 for x. So we plug in 9 for x. We get y equals plus or minus 3. Because y? Because 3 squared is 9, and negative 3 squared is 9. So we get 9 yields 3, but it also could yield negative 3. And so you could work out like 0 would go to 0, 1 would go to 1, and also 1 would go to negative 1. Because when you square, let's see, this is supposed to be y. So we're going to, whatever we get for x, y squared is equal to that. Yeah, so the problem here is, so like if you look, 3 squared is 9. 3 squared is 9. Negative 3 squared is 9. So the problem here is that you have 9 going to both 3 and negative 3, and that's bad. We have 1 going to both 1 and negative 1, and that's bad. It's not bad, it's just, that means that it's not a function. So y squared equals x is not a function. There's nothing bad. It's still a relation though, okay? Relation they don't care. So how would you realize this how would you know this with the idea of age, okay? Well, you can't have one person with 2 different ages. You can't have one person with 2 different ages. All right, so you don't want that. So that's how you can remember if it's a relation or a function or not, all right? Okay, so let's talk about notation for functions. So notation. So what if I have 2 functions that I call one of them y equals x squared, which just showed that that was a function. And what if we had y equals 3x plus 1? Let's say y equals mx plus b. This is your general line right here. This is a line. Okay. And what if I said, consider the function y? Let's consider the function y. Okay. Well, which one? You got 2. You got this y, and you got this y. So it'd be nice if they had different names, different letters representing them. So what I'll do is I'll say, well, that we're gonna call the first one f equals x squared, and we're gonna call the second one, let's say g equals mx plus b. I'm using f because the word function starts with the letter f, and then g comes after f. All right, so now we're okay. We just called them different letters, right? What's really more important is what's on the right, not what's on the left anyway. Now, if you look on the right over here, there's 3 letters, M, X, and B. And the question might be, well, which letter do I plug numbers into? So what I'm going to do is I'm going to tell the reader, X is the letter I want to plug numbers into. And the way you tell the reader that is you put X in parentheses. Okay, so this tells the reader that X is the variable. And then we just do that in general for all of them. So f of x equals x squared. So we say f of x, not f times x. This is not f times x. So sometimes whenever you put a number in front of x like that, this is 2x, this is times. But if you put a letter in front of it, like if you know it's a function, this is not times, okay? So not multiplication. All right. So anyway, so that's notation. So now that we have that notation down, what if you want to plug a number in? So what about plugging numbers in. Well, there's a way to write that down too. All right, so if you say, so f of, so let's say, so if k is a number, let's say a. No, k is good. If k is a number and f of x is a function, then f of k means plug k in. All right, plug k in. So for example, if I have f of x equals, I don't know, 4x minus 1, f of 2 would be 4 times 2 minus 1, which is 8 minus 1, which is 7. We can play this game with a lot of numbers. F of negative 1 would be 4 times negative 1 minus 1, which would be negative 4 minus 1, which would be negative 5. All right, so before I go on, the first one implies then that 2, 7 is a point on the graph. This implies then that negative 1, negative 5 is a point on the graph. So these are points on the graph of f of x equals 4x minus 1. Well, you might be like, well, why? Well, because if you just go back to letting, so the question might be, well, why? Well, if we go back to y equals 4x minus 1, and I say graph this, one way to graph it is just to plug in points. So if I were to plug in 2, I would get 4 times 2 minus 1 is 8 minus 1, which is 7. I get 7 here. And you know that 2, 7 is a point on the graph. Well, that's what we got before, 2, 7. So when you plug in f of 2 and you get 7, that means that 2, 7 is a point on the graph. Now let's go back. If I plugged in, let's say, negative 1, I'm plugging it into this. I do 4 times negative 1 minus 1 is negative 4 minus 1, which is negative 5. This is negative 5. So this means that negative 1, negative 5 is a point on the graph. And same thing here. I have f of negative 1 gave me negative 5. So negative 1, negative 5 is a point on the graph. All right, so it's real helpful if you know that. Now, sometimes they ask us to plug in unusual things. So suppose still that f of x is 4x minus 1. They might ask you to plug in f of a. Well, you just put a in for x and you're done. That's it. Or they might say find f of a plus h. Well, you just put in a plus h in for x minus 1. So what I'm doing is I'm taking the a plus h and I'm putting it in here for x. And it goes there. And then you just simplify it from here. So this becomes 4a plus 4h minus 1. This is done a lot later on in calculus. It comes from a very important formula. And here's the formula here. So I got this. F of a plus h minus f of a divided by h. It's probably the most important formula in most of elementary mathematics. Well, f of a plus h, I got that here. So that's 4a plus 4h minus 1 minus, and then 4a minus 1. That's from f of a. That's this piece here, which is this. So that's where I got 4a minus 1. This minus, the minus here is this minus here. All right, so we divide by h. And now we get 4a plus 4h minus 1 minus 4a plus 1 all over h. And now we get 4a's cancel, the 1's cancel, so we get 4h over h, which is just 4. And there we go. So this is a little bit difficult here, but I think if I gave it to you as a bonus on the test, I think you could probably do it. All right, so the next thing we're going to talk about is domain and range. So the domain of a function, the domain is basically, this is the x set, and the range is going to be the y set. So what I mean by that is whatever you plug in is going to be the x set. I'm calling it the x set. I don't know what they call it in general. And then whatever you get out is the y set. The reason I'm calling it that is because normally whenever you have the xy axis, the domain is affected by what's going on here on the x-axis, and the range is affected by what's going on here on the y-axis, okay? So we'll get to that in a second. But basically, the domain is the, so here's the definition. The domain of a function is the set of all real numbers which when plugged in, what does that say? I don't know what that says. Plugged in, yield a real number. All right. So we start out with real numbers, and they've got to get a real number out. So this is very simple for simple functions. So for example, if I were to say f of x equals x minus 3, whatever number you plug in for x will yield a real number out. So the domain of this function is all real numbers, because all real numbers will work. All real numbers, when plugged in, will yield a real number. Same thing is true for g of x equals x squared plus 5. Whatever you plug in for x will yield a number back on the x-axis. Same thing with x minus 3. Whatever you plug in for x will yield a number back on the x-axis. Same thing for g, all right? So this works for a lot of different functions. So this is also all real numbers, okay? All right, so when things don't work is, so what are some non-real numbers? Non-real numbers. Well, so because see, when you plug in a real number, you have to get a real number out. So what are some non-real numbers that would be obtained by plugging in real numbers? All right, so that might be a question. So this says sum. Well, two examples. The first example would be some number over 0, so anything over 0. This is undefined. And the second example would be the square root of a negative number. This is an imaginary number. This is not a real number, and neither is an undefined number. These are both non-real. All right, so imaginary numbers we're going to get to later, but I think you might have seen them in high school already. So when would you get an undefined number? Well, this example here, let me make this a little bigger. An example would be f of x equals something like x over x plus 3. So if you notice, if I don't want 0 here, 0 is not allowed down here. as an answer, okay? So if you set x plus 3 equal to 0, you'll find out the number that is not allowed, that you can't put in the domain. So apparently if you plug in -3, so f of -3, give you -3 over -3 plus 3, which is -3 over 0, and this is undefined. Undefined. So apparently -3 is not in the domain. Now it turns out that that's the only number that's in the domain, that's in the x-axis, that wouldn't work. Because you plug anything else in for x, and you'll be okay. All right? You may get a fraction out of it, but you'll be all right. Even plugging in 0, like if you plug in 0, so f of 0, remember that the function was x over x plus 3. If you plug in 0, you get 0 over 0 plus 3, which is 0 over 3, which is 0. That's okay. That's a real number. A real number is any number on the x-axis, any number on the number line. So this is okay. So the domain here is all real numbers except -3. All right. Except -3. Now the book wants you to write that in set notation, so that's the set of all x such that x is not equal to -3. So this first piece here means the set of all x. It's the set of all x in the real numbers, okay? Set of all real numbers. All right, so basically this is your answer. Now what if you had something like this? Let's change colors. Here's an example. What if you had g of x is something like square root of x plus 3, okay? So now what we want to keep the interior, it's called the radicand, keep the interior positive. No matter what you plug in, it's got to stay positive. Well, why don't we see where things go right? So a positive number, positive or, keep the interior or 0. Say, instead of saying the interior positive or 0, let's say keep the interior non-negative. Because 0 is a non-negative and it's not positive. So if you just set this greater than or equal to 0, this will be the domain. The domain is the solution to this. So let's see, x, if you subtract 3 from both sides, you get x greater than or equal to 3, which when you put this on a number line, here's -3, x is greater than or equal to it. It goes all the way to infinity, and so the domain would be -3 to infinity. There you go. Here's your domain. All right. So these are the numbers that do work. Let's look at numbers that wouldn't work. So a number that wouldn't work, let's say -4 is here. -4 is less than 3. -3, sorry. So let's plug -4 in. So we get g of -4 is the square root of -4 plus 3. Just plugging it in for x, which is the square root of -1, which is imaginary. Okay, and so we tried a number not in the interval, tried a number not in the interval, and it didn't work. So that's like an informal check. All right, so the bottom line is, if you're trying to find the domain, you, if it doesn't have a fraction in it, with x's in the bottom, you're good. All right, like up here, these guys, there's no fractions. And if it doesn't have a square root, you're good. The answer is just automatically all real numbers. I'm talking about a square root with an x in it. All right, now if it does have a fraction in it with letters on the bottom, with variables, you just set it equal to 0, and the numbers you get out, you may get more than one, are the numbers that you exclude from this expression, all real numbers. So that's what we did. We said all real numbers except -3. So now whenever it has a square root, you take the interior and you set it greater than or equal to 0. And you solve, that is the domain. Whatever you find, it is the domain. Okay? So try some of those examples in the book. Now, as far as what if the function's graphed? Well, if the function's graphed, then the domain, so we have some function here, maybe it stops here and here. So maybe it starts at -3 and ends at 5. It's probably 4. So the shadow of the graph over the x-axis is the domain. So this would be -3 to 4 right here. So if you were to compress this all the way to the x-axis, compress it all the way to the x-axis, that would be your domain. So here's your domain. Another way to think of it is all the x values, this is your x-axis, your y-axis, all the x values that correspond to the graph, here we go, these all correspond to the graph. Those are the ones that are in the domain. And then once you fall out of that, like over here at -4, once you fall out of that, that's not in the domain. While we're at it, the range is all the y values that do that. So if your function looks something like this, oops, can't do that. It stopped here, started here, it starts at -1 and ends up here at 4. And the range will be pretty much the shadow, the compression, compress it onto the y-axis. And you see what those numbers are. So the range is a set of all y values that correspond to the graph. So that would be from -1 to 4, like that. Now, while I'm at it, there's a line test that I need to tell you about. It's called the vertical line test. And it says this, vertical line test. It says if a function, let's say this, every function can, when graphed, can only intersect any vertical line at most once. At most once. So if it hits it twice, then it's not a function. So there's two examples I want to give you. So one example could be like this function here, and a vertical line will hit it only once. So that's a function. So this f of x is a function. So this is yes. Now if I give you something like this instead, where it kind of curves in on itself, then a vertical line will hit it twice. In fact, a lot of vertical lines would. Now you could say, well, this line doesn't, but that's okay. It says any vertical line. So this one is not a function. All right. And so that's functions.